All right, welcome to video 3 for the summer homework packet answer key for problem number 6, 7, and 8. All right, for problem 6, what we're doing is we're solving for variables. And in 6a, what we have is x plus a over y, x over a plus y over b plus z over c equals 1. And what we want to do is solve this function or this equation for the variable a. So the first thing I'm going to do is I'm going to subtract the non-a fractions to the right-hand side. And this should be subtract z over c. And then what we can do is we can take the reciprocal of both sides, and effectively what we're getting is a way to isolate the a. And then finally we multiply the x across, and we get a equals x over 1 minus y over b minus z over c. This, of course, is one of multiple approaches that we could take. Another approach, which I won't demonstrate, but we could find the least common denominator and then work from there. I don't think that method would be faster or better than this approach here. This one is sufficient. All right, 6b, we have the equation v equals 2 times AB plus BC plus CA, and we're solving it for A. So what we need to do is isolate the A. So the first thing that I'm going to do is I'm going to distribute that 2n, 2AB plus 2BC plus 2CA. Now I'm going to subtract the non-a terms to the other side of the equation. So v minus 2bc equals 2ab plus 2ca. And now I want to isolate the a. So one thing I can do is factor the a out so that the a is by itself. And finally, I can leave the a on the right-hand side and divide the 2b plus 2c to the left-hand side. And we have now solved for a. All right, the next one, 6c, says a equals 2 pi r squared plus 2 pi rh, and we're solving for positive values of r. And this problem might look a little bit difficult to start off with. It's kind of difficult to isolate the r. We could factor an r out, but then we have r in both terms. So what I'm going to do is do a little bit of manipulation here, and maybe it'll become more clear to you. The first thing I'll do is I'll subtract a to the right-hand side. 2 pi r squared plus 2 pi r h minus a. And what we have here, if we think about it a little bit, what we have is a quadratic equation. We have number x squared plus number times x plus number. So ax squared plus bx plus c. And that allows us to use the quadratic formula to solve for when that quadratic equals 0. So as a reminder, the quadratic is negative b plus or minus b squared minus 4ac all over 2a. So we want to start filling this in. Our b value is, well, let's go ahead and write these down. Our a value is 2 pi. Our b value is 2 pi h, and our c value is negative a. So when we go to fill out the quadratic formula, negative b would be negative 2 pi h plus or minus the square root of b squared minus 4 a c all over 2a. Now we have a quadratic formula that we can work at simplifying. So let's shrink this down and try to simplify this as best we can. So negative 2 pi h, can't do anything to that, plus or minus, the inside would be 4 pi squared h squared minus plus 8 pi a all over 4 pi. And this equals r. Now there's probably various tricks we could do to simplify the radicand, but nothing really cleans it up that much. We can't cancel these pi's here because we'd have to cancel a pi here and a pi here as well, and we can't really cancel into a radicand. So this is as simplified as it can get. The question, however, does specify for positive r values, and if we start to think about that, what we could say is, well, this is negative, so a negative value subtract a number will keep this all negative as well. So we need to get rid of the subtract for our final answer, 2 pi h plus 4 pi squared h squared plus 8 pi 8 all over 4 pi. And this should get us a positive r value. Of course, it would depend on what are the a's and the h's, but overall this should wind up creating a positive value. This was a tricky one, but it was a creative way of saying, hey, do you remember the quadratic formula? And if you don't remember the quadratic formula, you need to memorize that, because that tells us the zeros of a quadratic equation. All right, 6D is actually much easier. A equals P plus NR times P, and we are solving this for P. So since we have P in both terms on the right-hand side, what we can do is factor the P out, and we get 1 plus NR. And then we can divide the second term to the left-hand side, or the second factor, and we get our final answer much, much quicker. All right, 6E, that one is not too bad either. We start out with 2x minus 2yd equals y plus xd, and we want to isolate the d. So what I'm going to do is I'm going to move all the d terms to the right-hand side of the equation and all of the non-d terms to the left-hand side. And what that does is it allows me to factor a d out of the equation, or the right-hand expression. So by factoring that d out, I can then divide the second term to the left side. 2x minus y over 2y plus x is equal to d. There we go. Solved for D. Okay, the final one, 6F, we are solving for x. And one of the things that I notice is I've got some fractions here. So the first thing I'm going to do is try to get rid of the fractions, which is really easy to do when you don't have any variables in the denominator. So since I have 4 pi and 2 and 1 in the denominators, it's pretty straightforward to get rid of the denominators. And you can do this in one step if you wanted to, but I'll go ahead and do it in two. First thing I'll do is I'll multiply everything by 4 pi. And what that does is gets rid of the first denominator. And then I'll multiply everything by 2 to get rid of the second denominator, giving us 4x plus 4 pi times 1 minus x equals 0 times 2. Or another way of writing that, 4x plus 4 pi minus 4 pi x equals 0. We can then factor out the x and move the 4 pi across, so we get x times 4 minus 4 pi equals negative 4 pi. So the 4x and the minus 4 pi x is this piece right here. And then from there we can shrink that, divide the 4 minus 4 pi across. So x equals negative 4 pi over 4 minus 4 pi. If I factored a 4 out of the top and bottom, I would find that this is equal to negative pi over 1 minus pi. So either answer is acceptable. This is the more simplified answer, and you could even simplify that further if you wanted to. Actually, I think that's about as simple as it can get. So let's take a look at the next problem. How can this be true? Alright, in problem 7 we're doing some factoring, my favorite. Factoring is one of the most important skills because it keeps coming back all the time, and we're asked to factor things to solve. This one we're given is x to the 6th minus 16x to the 4th. And the first step in factoring is always to factor out your greatest common factor, and in this case x to the 4th is our greatest common factor. So if we pull that out of the first term, we are left with x squared, and if we pull it out of the second term, we're left with 16. And there's our first step in factoring. Then we need to see if anything else factors further down. And in this case, we have a difference of squares right here. So we can factor that to be x minus 4 times x plus 4. Difference of squares. There we go, fully factored. Alright, 7b. This one's a little bit harder to factor, and we have 4 terms, and it's a third degree polynomial. So because of that, I'm going to think possibly factor by grouping. And so the way that works is I look at the first two and I look at the second two. And for the first two, the greatest common factor that I see is 4x squared, and that leaves me with x minus 2. That's just the first two terms. The second two terms, the greatest common factor I see is negative 25, and when I do that, I'm left with negative 25 times x minus 2. And we're on our way. This is pretty cool because this term and this term are the same. If they are different, factor by grouping either doesn't work or you made a mistake along the way, or you maybe didn't factor out as much as you needed to. So with that, we can move that x minus 2 to the front, and then we're left with 4x squared minus 25. And finally, to finish this out, we check to see if either of our terms can be factored down further. And in this case, our second term is a difference of squares. So that factors to 2x minus 5 times 2x plus 5. Okay, for 7c, we are looking at two terms, 8x to the third plus 27. And this here looks like we have the sum of cubes. In other words, 8x to the third is the same thing as 2x, all raised to the third power. And 27 is 3 raised to the third power. And the often forgot factoring rule for the sum of cubes, I'll write off here to the side, a to the third plus b to the third is equal to a plus b times a squared minus ab plus b squared. And we can apply that here. In this case, our a is 2x and our b is 3. So when we factor this out, we're going to get 2x plus 3, 2x squared, 2x times 3, and 3 squared. Cleaning up the longer factor, we get quantity 2x plus 3 times quantity 4x squared minus 6x plus 9. And there we have a factored sum of cubes. There's also a difference of cubes formula that I'll write down here for your own reference in case we come across it. If it's a to the third minus b to the third, then what this factors to is a minus b, a squared plus ab plus b squared. All right, those are two factor rules which don't pop up too often, but when they do, it's very useful to know that rule. All right, finally 7d, we have x to the fourth minus 1, and this looks like a difference of squares as well. If you're not seeing it, what we have is x squared minus 1 squared. And since we have a difference of squares, we can write that as the first minus the second times the first plus the second. There's our difference of squares, and then we can apply that further to the first term to become first minus second, first plus second. And the second term doesn't get factored down any further, or cannot be factored any further. There we go, 7d. And it looks like 7a, b, and c apply to the next problem number 8. So I'm going to use our work to continue with problem number 8. How can this be true? I'll show you. Et voila. Okay, for problem 8, we are taking the same equation and setting it equal to 0 to solve for x. So we can either start at the beginning or we can start at our factored form. I find that oftentimes it's easier to start with the factored form. And if we're going to do that, what we're going to say is x to the fourth times x minus 4 times x plus 4 is equal to 0. And we can apply the zero product property, which means either the first term equals 0, the second term equals 0, or the third term equals 0. And in this case, we're going to get three answers. And those answers are x equals 0, 4, and negative 4. So those are the three values that if you plug into this equation, it would set it equal to 0. Okay, we're going to take a similar approach for 8b. Once we have the equation factored, what we can do is, in order to set it equal to 0, we apply the zero product property. So either the first term is equal to 0, the second term is equal to 0, or the third term is equal to 0. And that gives us three answers, either x equals 2, x equals 5 halves, or x equals negative 5 halves. So there's our three answers for 8b. Okay, for 8c, we could try using the zero product property again, which means we'd either set the first term equal to 0 and the second term equal to 0. However, in this case, setting the second term equal to 0 could be somewhat difficult. So I'm going to take a different approach, and it really is the fact that this is a sum of cubes that allows for this approach. It is actually faster and easier. If you start out with 8x cubed plus 27 and you want to set it equal to 0, let's isolate the x. So first we subtract the 27 across, then we divide the 8 across, and then finally we take the cube root of both sides. And if we do that, what we get is x is equal to the cube root of negative 27/8, which is, let's see, the cube root of 27 is 3, and the cube root of 8 is 2. So there's our answer, negative 3 halves. If we use the zero product property, we would see that we get a negative 3 halves from the first term. The second term, if we tried to set that equal to 0, we would probably get some complex roots. Because remember, a polynomial will always have the number of roots as the degree. So since this is a degree 3 polynomial, we're going to have the one real root that we've just discovered, and then 2 more complex roots. Okay, this concludes the video. Thanks for watching, and tune in for the next one coming shortly.